Let's review what we did yesterday. And so yesterday we had our map that looked like this: 0, 1, 0, 1. Here we have 1/2. Here we have 1/3. Here we have 2/3. And then our map. And then we define lambda is by definition the set of points that stay in 0, 1 for all n. And then we had sigma 2 plus, I can't remember where the 2 was, the plus was 2 plus, is equal to the set of sequences of zeros and ones. And then we showed that there is a bijection. There exists a bijection. In fact, there exists a conjugacy. Right? So there exists a bijection pi from which direction do we define it? For bijection, it doesn't really matter, but we define it like this to this, okay, such that pi composed with pi composed with sigma equals f composed with pi. Okay, where f is restricted to lambda. It's clear. And this gives us a lot of information, right? The dynamics, we looked a little bit at the dynamics of this. We saw that it has under the shift map. So sigma is the shift map. So here we have f lambda to lambda. And here we have the shift map, sigma 2 plus to sigma 2 plus. There's lots of periodic orbits. We would like to have some topological structure in sigma 2 plus, so that we can, for example, talk about the omega limits of orbits in here, right? Because not all points are periodic. Like the periodic points are the points where you have repeated things, but lots of sequences are not periodic in the shift map. So we'd like to talk about the omega limits, right? So we want topology in both sets. So what is the topology on lambda that we consider? Lambda is a subset here.
So that's subspace topology?
Subspace topology, right? So we can just define the topology that is induced by the metric on your Euclidean metric here, right? So it's a subset of R, so you just take 2 points and you can put a metric on that, which is just the distance, the actual distance between the 2 points in the line, okay? So it's very simple. What about sigma 2 plus? What's the topology we can put on this? Have you ever seen this?
Topology lambda by
your product looks like because it's a product of looks like Equivalence theorem or a product of discrete topology or something like that.
Okay.
But we can also borrow it from lambda by this bijection. We can define a subset of the sigma is open if and only if its image is open.
I'm not sure about that. Maybe
It makes it
because
makes it homomorphic.
it makes it by automatically forced homomorphism, but then we would have to make sure we understand what topology that gives. Okay. Instead, we're going to define a topology that makes sense, and we're going to show that it's a homomorphism with that topology, right? Which is exactly as you say. So there is a natural topology, which comes from the observation that in fact you can write sigma 2 plus is equal to 0, 1 is a product space in this sense, right? Because it's the product of infinite copies of 0, 1, and there's a product topology but this topology is not so easy to visualize or to feel, but basically it says that two sequences are close if they coincide for the first 1 million digits, for example. Right? But we're going to define a metric which makes it a little bit easier to work with, okay? Just to be a little bit more precise, that induces the same topology. So there's many different metrics we can define. One of the simplest one is this. So let's write a metric. So we define a metric, D, metric and sigma 2 plus. And let's define this metric like this. The distance between two sequences A and B is equal to the sum from I equals 0 to infinity of AI minus BI over 2 to the I. So why does the sequence converge? Clearly this sequence converges because the numerator is always only 0 or 1. Okay, because these here are 0 or 1. And so this is bounded above by the sequence 1 over 2 to the I, which converges. Okay, so this always converges. I will let you, again, I will not go through it, but you can check that it's a metric exercise. You can verify that it's a metric. Okay, and the most important thing is to realize what it means for two sequences to be close in this metric. Right? When are two sequences close? Clearly, because of the 2 to the I, when you take this converging sum, it is converging exponentially fast. So it's, well, in any converging sum, but in this particular case, you have this convergence, so the initial terms are the ones that count the most, right? So if you want this to be less than epsilon, then you must have AI equals BI for a very large number of terms, right? So let me write this as a remark. So distance between A and B is less than equal to epsilon if and only if AI equals BI for all I less than some n that depends on epsilon, which you could calculate explicitly in principle. Right? So you can actually calculate this n epsilon. Maybe I should write this even as a lemma. You can calculate some n epsilon that says that if these are less than epsilon, then it means these must coincide for a certain number of terms, because what you want is the tail of this to be less than epsilon, right? So if the tail is less than epsilon, if the first terms are 0, then you know that this sum is less than epsilon. And then, of course, if these AI and BI are the same for some sufficiently big number, then this is going to be sufficiently close. So it's clearly it's the same. So this is the way to think about these sequences, right? So it's a very natural way to think about it. Just like as someone mentioned that when you look at decimal expansions of real numbers. Okay, there is a crucial but subtle distinction between the Euclidean metric and this metric, which will be interesting. I will make a comment about that later. It's not exactly the same thing, because if you remember, in the real numbers, not every point has a unique decimal expansion, right? This will be related to something we're going to do in a second. But at the moment, we have this property here. So we have a topology. You can check that this topology corresponds to this, because I said this topology, the two sequences are close if they coincide for a large number of iterations, a large number of initial places, so it induces the same topology. And using this topology, we can prove several things. So for example, we can prove that the periodic points of sigma are dense. Why is that? So we need the topology to talk about denseness, right?
Yeah, because we can take it to the thing we repeat, we can take it as long as we can.
Exactly. Okay, so you take any sequence you want, okay, and clearly you can approximate this sequence by periodic points, because you just take the first 1,000 digits and you repeat them, and you get a periodic point of period 1000 or 1 million. For any epsilon, you just take sufficiently many digits, and then you know that that point, any point that starts with those digits will be epsilon close, and then you just repeat them and you make it periodic. Okay, so immediately you have that. And then you have that there exists A in sigma 2 plus, such that the omega limit set of A is also. So there exists a point with dense orbit.
We enumerate all the finite.
Exactly.
And concatenate.
Exactly. Okay, exactly the same thing that we did. So you need to concatenate all the finite. So here you concatenate all finite blocks. For example, you get A bar equals 0, 1, then 0, 0, 0, 1, 1, 0, 1, 1. Like these are all, so this is length 1, then this is length 2, and there's 4 possibilities, and then you take 0, 0, 0, 0, 0, 1, all the way to 1, 1, 1, and then you start with the blocks of length 4 and so on, right? And then you see that when you take the shift map, right, sooner or later you will get any block you want at the beginning, right? So if you want to show that eventually that some arbitrary point is in the omega limit set, then well, you need to show that for any epsilon, at some point the iterate of this will come within epsilon. Okay? So using this remark here, you say, well, to be within epsilon, I need to coincide for the first n epsilon iterations. Okay? So you look at the first n epsilon digits here, and you say, I need to make sure that there's some iterate of this that starts with exactly those n epsilon digits. So all I need to know is that that block of length n epsilon occurs somewhere in this digit, okay, in this sequence, and I have every single finite block, so I can find that one there. Okay. So this is really very remarkable. This is a dynamical system in itself. There's space and the dynamics that it creates, and there's a whole kind of area of dynamical systems, symbolic dynamics, that just studies this map on this space. Yeah, there's actually lots of things to say. In some sense, not that many anymore. You know, it's kind of been studied, but there is a lot of study. And you can do it, we will see in a second, you can do it for more than 2 digits and so on. I will talk a little bit about the generalizations. But first, now that we have this property, if we show that this is actually a topology, now we have a metric on both sides, we have a topology on both sides, so we can check whether this bijection is continuous in both directions. If it's continuous, then it's a homeomorphism. Right? And if it's a homeomorphism, then this is a topological conjugacy, and if it's a topological conjugacy, then, for example, this property, the fact that there is a dense orbit, this is transitive, right? There's a definition of transitive, so this system is transitive. Then F on lambda is also transitive, so in this set lambda, there also exist points whose orbit is dense in lambda. Okay, so we kind of push that information from the symbolic dynamics onto the space. So I will leave it as an exercise. We can discuss it a little bit, but lemma is now that pi from sigma 2 plus to lambda is a homeomorphism. Let me leave it as an exercise. But why do you think it's a homeomorphism? Let's try to look at the continuity. Okay? Continuity in this direction. So what do we just epsilon delta definition of continuity? Right? Suppose we take 2 sequences that are very close in this space. What does it mean?
They agree in the first.
They agree the first 1,000 iterates. Okay? So now we need to show that if you take 2 sequences that agree within 1,000 iterates, then the corresponding points in lambda are very close to each other. And why is that? Exactly. We did the estimate last time, right? The interval I, A0 to A1000, is of size 3 to the minus 1000. So it's very small. Okay? So that you show continuity in that direction. In the other direction, if you take 2 points that are very close here, how do you know that they will have the sequences that coincide for a very long time? Sorry? This is just really basically continuity of this map. If 2 points are sufficiently close, they will stay close for an arbitrarily long time. And if they stay close for an arbitrarily long time, it means that their combinatorics in terms of I0 and I1 stays the same for a very long time, which is what gives you the simple sequence of those points, right? So if 2 points are far away like this, then the next, this one stays in I0 and this one stays in I1. But if they're very close, this cannot happen. You know, if they're close enough, they will stay together, and then eventually they will go further, they will move further apart. Okay, so but make sure you write down the argument for this, okay? But I just wanted to sketch this. Very good. So we have proved, okay, that I think that's what I wrote as a theorem. Did I write as a theorem last time? That this, did I write it? That they are topologically conjugate? No, I didn't write it. Anyway, so conclusion, theorem, okay, theorem. F restricted to lambda and sigma restricted to sigma 2 plus are topologically conjugate. Okay, so now I'm going to ask you how we can generalize this. First of all, notice that what are the ingredients we used? Suppose we have a map like this. So suppose that we have 0, 1 to 0, 1, and suppose we have a certain number of disjoint intervals, I0, I1, I2, I3, for example, right? And suppose that we know that the map from I0 to I1 is a diffeomorphism. Let's not make it affine, we just suppose that it is a diffeomorphism of some kind. Okay, and then we can fill in. If we want this map to be defined everywhere, if we want, we can fill it in, but it doesn't really matter, right? Because so here it doesn't matter if it goes down or up, right? It's the same. We can have it going up, we can have it going down, which is how we had it before. Okay, so if we want, we could fill it in, and we could suppose that the map actually does something like this, and then it does something like this, and then it does whatever we want to do here. But this doesn't matter if we're interested in just the points that stay inside here. So let me write this down properly. So let F 0, 1 to 0, 1 such that there exists disjoint closed intervals I0, ik minus 1. Okay, such that F restricted to each of these ij's from ij to 0, 1 is a diffeomorphism. Is that clear what I've written? Yes? So you restrict it to each ij. The map maps ij diffeomorphically to all of 0, 1. Okay? And then we can let lambda equals the set of points x such that fn of x lies in the union of all these ik's for all n greater than or equal to 0. Okay, this is direct generalization of what we had before. In some sense, before we had a globally defined map, and we noticed that points that go outside those I0 and I1, they escape and they went to infinity. But suppose it doesn't matter. Maybe these points, they do something that is relevant. But we decide we're not interested in. We are only interested in the points that stay inside these intervals for all time. As soon as they jump out, it doesn't matter what happens to them. We're just not going to consider them anymore. Okay? And then we would like to prove theorem is that f restricted to lambda and the shift map restricted now to sigma k plus. So sigma k plus is the same thing, so maybe I should write it here. Sigma k plus is equal to the sequences a bar equals a0, a1, a2, such that ai is in 0 to k minus 1. And here, sorry, I should also, okay, there is an obvious, you define the metric exactly with the same way, but with k instead of 2, like k to the minus I, ai minus bi, and you get exactly the same thing. And these are topologically conjugate. Is this correct? Is this true? Let's just quickly think through the various steps of the argument. So let me clean up this picture a little bit so we just see the map on these intervals. Okay, this is the map. These are the intervals. Can we do the same construction? Yes? So we just define in the same way we define the same intervals, I, A0, A1, A2, finite numbers, just the set of points that have that particular sequence. And if you see, if we do the same construction and we draw here the equivalent, we draw here I0, I1, I2, I3, you see that each one of these has 4 subintervals inside them, right? This is the set of points that are in I0 that map to I0. Here's the set of points I01 which map to I1, I02 which maps to I2, I03 which maps to I3. And you can do the same for all of them, right? This is I1 that maps to I0 will give you a small interval here which is I10, I11, I12, I13, and you get all the possible combinations exactly in the same way we had before. But then there was some crucial thing. Remember, we needed to show that these were shrinking to 0. How did we show that we're shrinking to 0?
You see, we use the derivatives to show that the derivative is the derivative of the iteration is was 3n.
Exactly, but now it's no longer.
Yes, but it is diffeomorphism, so therefore the derivative is bound.
Bounded what? By what? Diffeomorphism just means that it is bounded from 0.
Yeah.
But 0 is not good enough to get the shrinking.
Yeah, for us, it implied in the last time, it implied uniqueness and the correspondence between this coding and
That's
this
right,
intersection.
exactly.
So it can happen, it may happen that this coding is not unique.
Well, in principle, it might happen that these intervals are not shrinking to 0. Right? So we can add one more assumption. What assumption do we need to add?
infimum of the length of intervals is bigger than 0. Some maybe infimum of the length of infimum of the intervals. I mean length of intervals
of these ones.
Yes.
But these are just finite, so it's clear that they are the infimum is the length.
A1, A0, A1, A2.
What did we use instead of that? 3. Remember when we did that calculation with 3, I said what we're using here is the chain rule and the mean value theorem. Remember? And so what do we need? First of all, we don't need 3, we just need something bigger than 1. Right? Because what we had is this 3 to the n, and we just need something bigger than 1 because it needs to shrink. Or 1 over 3 to the n we got. And then the chain rule, I'm going to leave this as an exercise, but what you need here is that we want to assume that f prime of x is greater than or equal to some lambda greater than 1 for all x inside the union of these intervals. In other words, that the derivative everywhere is bigger than 1 in absolute value. Okay? And if you do that, which I want you to do as an exercise, you look at that part of the calculation that we did, then you see that that's exactly enough. Okay? Because if you do that, then by the chain rule, it means that the nth derivative is bigger than lambda to the n. Okay? And if you remember, that's all we used. If you will look at the size of one of these little intervals, a0 to an, then it was less than or equal to 1 over the derivative times 0, 1, which in this case would give 1 over lambda to the n. Okay, I specifically don't want to write it because I want you to do this as an exercise. Okay? In fact, you even need a little bit less, but let's not go. You can generalize even more. You just need eventually the derivative to be growing. So you can even put a little bit. But this is a very natural condition. All it says is that you need not only this to be a diffeo, but an expanding map. This is what's called an expanding map. It's at every point it's expanding, because if the derivative is bigger than 1 everywhere, then locally, if you take any point and you take its neighborhood and you look at the size of the image, it will be bigger than this by a factor lambda. Okay, again, this is the mean value theorem. In particular, it means that every pre-image of every set is less than 1 over lambda times the size of that set. Okay, so this is called an expanding map, because the derivative is bigger than 1 everywhere. So this is the theorem. This is really the general result. Okay, at least when these intervals are disjoint. So let me make a few more comments before moving on from this situation. The first comment is that this obviously implies that you can create a topological conjugacy between maps, right, of this kind. So if you have two maps, where one of them looks like this, right, and the other one looks like this. Okay, so this one has this interval here, so this one has an interval here, I0, this one has an interval I1, okay, this one has an interval I2, and this is the same, I0, I1, I2, this is F, this is G, then we can construct F restricted to lambda of F, defined in the same way, and G restricted to lambda of G, and these will be topologically conjugate. Why is that?
Because of we can draw the graph. We have a map from to sigma k plus, and k is same.
Exactly, because it's an equivalence relation. So both of these are topologically conjugate to sigma 3 plus in this case, and so they're topologically conjugate to each other.
But what if the k's are different?
Good question. What if the k's are different? Can they be
I
topologically
have
conjugate?
a map which is, because every such sequence correspond to a unique real number. For example, if I have 2, I use the binary this representation.
Yes.
So if I have k and f, every sequence corresponds to a real number, and on the real numbers I have the identity.
Yes.
So I can take this identity to be a map between those two classes of sequences.
I'm not following, but are you trying to say that they are or that they're not?
I have a function, but I'm not sure if it is homomorphism or not. It is just
So you're trying to show that they're still conjugate, even if they have different number of branches.
if this function is a natural function, I don't know.
But you're trying to argue that they are conjugate. Okay, think about a very simple reason why they cannot be conjugate.
In the case of K1 and K2?
For different, if they have different number of branches, why can they not be conjugate?
Because I can take the identity and K equal to...
No. Why
Fixed
not?
points.
Yes, exactly. They have different number of fixed points. Right? Because there's one fixed point for each branch. You can see it either in the map or in the symbolic dynamics. So if sigma k plus has exactly k fixed points because it's got the zeros, the ones, the twos, and if you have another map with a different k, it will have a different number of fixed points. Okay? So that's a good question. So the two maps of this kind are conjugate if and only if they have the same number of branches. Does it depend on the orientation? So if I take one with negative derivative and 2 with positive, and here I take all 3 with positive. Or even more simply, in the case with 2, if I take this, or if I take this.
It doesn't matter for example, for sigma k, it doesn't matter.
Exactly. Because we just did the whole construction and we realized that there's no, in both cases, the construction gives conjugacy with sigma k. So they have to be conjugate. Okay? Good. So now we're going to move on to what we really want to do, which is look at when we close these gaps. Okay? Something a little bit more complicated happens because these are, in some sense, this was kind of a case study, okay? Because here it's very nice because you get a perfect conjugacy with the shift map, and a little bit more difficult is what happens when we close the gaps. So let me draw a picture here. So let's start again with the same map that we do the first time. Okay. So we have this map like this. Okay. And we have our intervals. This is 0. This is 1, this is our intervals I0 and I1. Now, what happens if we change this a little bit and we make the gap very small? Right, So now we have the intervals I0 and I1 are like this. Well, as long as there's a gap, there's no difference. We don't know. When we do this topological conjugacy, we just look basically at the topology. We don't worry about the actual sizes of the gaps. Okay, we worry just about continuity. But what is happening here if we close the gap? In other words, what happens now, this is the case we really want to study, is the so-called tent map, in which we have so this is sometimes called tent map. In fact, they're all called sometimes the family of tent maps, but because they look like a tent, but this one is most usually called the tent map. So this is Tx equals 2x if x is less than half and 2 of x minus, is it 1 minus x or x minus 1 here, 2, 1 minus x, right, when x is 1 half, yes, x is taken like this. So what goes wrong? How do we, can we do a similar thing, a similar construction? It's a bit tricky because now if I0 and I1, they kind of intersect at the boundary. Right? So we could still, in some sense, have I0 and I1. And now notice that lambda is the whole set. Now if you define lambda is equal to the set of points where fn of x stays in 0, 1 for all n, right, then in this case it's everything. So there's no problem anymore in describing what the lambda set is, but we still want to study the dynamics on the set lambda. Okay, so we still want to understand similar things that we tried to understand before. Intuitively, it should be pretty similar, right? We had periodic points everywhere, we had dense orbits and so on. Not much should have changed just at that moment, okay? But how can we really implement the same procedure? It's only really a little bit, you can do it, you just have to be a little bit careful about these points, because many points will never intersect this boundary point. So many points they will keep, you can still code the points depending on whether they go in I0 or I1. The problem is when the point falls on this. So what is this point? What is the symbol associated to this point? Is it 0 or is it 1?
It will be 1, 0, 0, 0, 0, 0.
You mean you think of it as being belonging to I1? We don't know. It belongs to both.
And one,
Because there's a closing.
like it be like one half like at the unit.
Excuse me?
Maybe not because it's not.
Well, so let's think about the codings here of these points, right? So what is the coding of this point here, this boundary point here?
0, 0, 0, 0.
Exactly. This point here is 0, 0, 0. What is the coding of this point here?
All ones?
No.
1, 0, 0.
Yeah. This is 1 and then zeros, because this belongs to I1, but its image is 0, and then it stays 0 all the time, right? So this is 1, 0 recurve. Sorry, 0, yeah, 0 recurve. This is 0 recurve. Okay? What is the coding of this point? 1, then its image is 1, 1, 1, and then 0, right? So, here put 0, 1. So this here is 1, 1, 0 recurve. Okay? What is the coding of this point? 0, 1, and then 0 recurve. So now, let's just look. So, in some sense, the problem is, so what's the difference between these two? What's the difference between these 2 points?
The first entry?
It's just the first entry, exactly. So, So let's see. Let's do it. Let's do one more step. I'm trying to think of how. Okay, so let's think now about the other endpoints. So when we go one step further, right? So we get here we get I00, and here we have I01, right? And then here we get I11, and then here we have I10. Okay? Those are the 4 intervals of the next level down. So let's look at the boundary points here. What are the boundary points? What's the coding of this? This starts with 0, and then
It is also 0.
it is also 0, and then 1, because it falls onto the point 1, right? So this boundary point is going to finish with 1, 0 bar, right? Because this point, is that right? Did we do it right? So this is 0, and then it maps to it maps to here. So after 0, it maps to here. So it takes on this sequence. Okay. Once you land on a point that you know, that's what comes after that. Okay. So here is just 0, and then the image will be this. So it carries on this. What about this? This is I01, and when you iterate it, it maps onto this, right? So this endpoint, it maps here, which means that this is, sorry. This endpoint first maps to 0, 1, and then it maps to all of the whole interval, right? So this point here starts with 0, then 1, and then it maps to this, which is 0, 1 bar, like this. Is that okay? Because this point, this interval, so here we have this is I0, and this here is I1. Okay, so the coding for this point here, which is on the boundary of I0, is I1, 0 recurring, and this point here has 1, 1, 0 recurring. This one here is 1, 0 recurring. Okay, and so this point here, it maps to this. Okay, so this end point here starts with 0, and then it maps to this solid. So that should have been 0, 1, 1. Is that right? So because this maps to this, so it means this endpoint maps to this endpoint, and this endpoint is exactly this endpoint, and the coding for this endpoint is 1, 1, 0 recurring. So I made a mistake there, but it's okay like this. Okay? So it's a little bit of calculation. So let's see. So, well, let's do it also for this, just to make sure we understand fully. So here we have this interval here. This is I11. So this boundary point starts with 1, right? And then the image of this is this, right? So this maps to this. This will map to this endpoint, which is 1, 1, 0 bar. So this is 1, 1, 1, 0 bar. Okay? And this endpoint, this one instead maps to here, right? So this small interval maps to I0, because this is I1, I0. So this maps bijectively to I0. So this endpoint maps to this. So this endpoint here is going to be 1, 0, 1, 0. Okay, so we're not going to go through completely, but what we're going to notice is what is the relation between the endpoints which we glue together. You see, what happens when you close, if you think about closing this map, then what is this going to do? This is going to glue together this point and this point, right? This gap is going to come together, and what happens to the other gaps? This gap is going to close at the same time, right? And this gap is going to close at the same time, because this gap is exactly These two gaps are the pre-images of this gap, right? So when you are closing this gap here, you're simultaneously closing all the other gaps. Okay? The structure of lambda is a Cantor set, and a Cantor set on the real line. What is the complement of the Cantor set? Have you ever studied?
Complement again Cantor set.
The complement of the Cantor set in the real line
Complement.
is a union of intervals. It's all the gaps. And how many gaps do you have in the complement of the Cantor set? No, you have a countable number of gaps. You cannot have an uncountable number of intervals. Okay? And these are exactly all the gaps that come from all the pre-images of this, right? At this level, you can see in this construction, you can see these gaps. This is the big gap, then it's got two little gaps, and then inside here there will be two smaller gaps, and you're building up all this countable number of gaps. Okay? So the Cantor set has this very unintuitive structure where it's made up by a uncountable number of points. Okay? But only a countable number of those are on the boundary, in some sense, of the Cantor set. If you look at the complement is a countable union of intervals, and each of these intervals has boundary points. Okay, so there's a countable number of points which are boundary points. So what we're doing here is, when we go from this picture to this picture, is we're just gluing together all the corresponding boundary points of this Cantor set. Right? So we're only affecting a countable number of points, okay, which are all the points which are actually pre-images of this one here, which are exactly the pre-images, which are all the gluing together all the gaps, and each one, now this gap becomes a single point, and this gap becomes a single point, and this point is going to map to 1/2, just like this gap mapped to this gap. In this case, this corresponds to the point 1/2. So this is the point 1/2, and there will be a point in the middle here which maps to 1/2, and another point in the middle here, and this is where you've glued together this gap here. Okay? And then all the pre-images of 1/2 are also the points in which there was a gap and we glued it together. Okay? Yeah? So what exactly are we doing in terms of the coding? So that's a kind of geometric intuition for what's happening when you're closing. You're going from having a Cantor set with gaps to having a full interval. You have squeezed each gap into a single point, but by doing that, you have identified those 2 points on the boundary of the Cantor set, right? So this point here belonged to the Cantor set, and it had this coding here. This point here belonged to the Cantor set, and it had this coding, and you're gluing together those 2 points. Okay? So you're gluing together 2 points, and what is the relation between the coding of these 2 points? One starts with 0, 1, and then all zeros, and the other one starts with 1, 1, all zeros. Okay? What about these 2 boundary points? So what is the corresponding coding of these 2 points? So these 2 points, they both start with 0 because they both belong to 0. Okay? But then, after the 0, we have exactly each of these maps to one of these 2, right? Because that's how they're constructed. This one here maps to this, and this one here maps to this. So this point maps to this point maps to this, and you can see it from the coding is that this one has a 0 followed by the coding of this point, and this one has a 0 followed by the coding of this point. Right? And the same thing on the other side. So here we have a 0, but then we have this coding, and here we have a 1, but then we have this coding. Right? So this is the coding of this point, and this is the coding of this point. Yes. So now, when you look at the pre-images of this, what will happen? Now, let's see if we can now... this is again where we don't want to start doing everything too concretely, but if you now think about what's going to happen when you do the next step, without doing it concretely, you see that there's not going to be any problem here. I mean, well, here when there's no gaps, eventually, because of the way these intervals are defined, at some point, these two endpoints that are facing each other across a gap, they're going to eventually fall exactly on these 2 points, because all the gaps, they have the property that sooner or later they fall exactly on this gap. Okay? So if you look at any level of the counter set, and you look at a gap, and you look at the 2 points that are facing each other, and you iterate these 2 points, after some iterates they're going to fall. One's going to fall here, and one's going to fall there. Okay? And before that, they're going to stay together. So they're going to have exactly the same sequence, because this whole thing stays together, and these two are going to fall on opposite sides exactly when the interval that contains them falls onto 0, 1. So these two, at every level of the counter set, you have this property. You take a little gap, you take the 2 boundary points, and they stay together for a certain number of times, and then at some point they fall exactly on these two. Yeah, you can see this happening? Yes? Good. So you can see exactly which ones we're going to be identifying, right? So basically we identify all the points. So what are the sequences that we identify? So when we, at the moment I'm still expressing this as a kind of intuitive level. So when we close the gap, let's write it like this, because when we close the gap, we identify. So, or let me try to write it a little bit more formally. We define, we let x be kind of identified with y. We define a kind of a equivalence relation, if you want. Okay, where we say that x is identified with y if let's see if I can write this. So we have the sequence a bar of x is equal to a0, a1, a2, and so on, and then we have the sequence b bar of y is equal to b0, b1, b2. Okay, and what do we say about these two sequences in order to describe the fact that they are the 2 points that are facing each other across a gap in the counter set? No, in terms of the sequence. We look at these sequences, right? And what do we need to see in the sequences? Say, we need to identify those points. What are we going to see about the sequences? So the sequences are going to have this property that they're going to be the same for a certain number of times. So there exists, let's say, some n, okay, greater than or equal to 0, such that ai equals bi for all I less than or equal to n. Okay, for example, in this case, it's just the first one, n is equal to 0, right? So the first one, and then we have that an and an plus 1. How shall we write it? Let's say that the sequence an plus 1, an plus 2. So the remaining part of the sequence is exactly equal to 0, 1, 0 bar, and bn and bm plus 1, bm plus 2. So the remaining part of the sequence, this should be m plus 1, m plus 2, m plus 3, m plus 1, m plus 2, m plus 3. So we have that they're the same up to a certain point, and then from then on, one of them is 0, 1, 0 bar, and the other one is 1, 1, 0 bar. 0, 1, 0 bar, and this one is equal to 1, 1, 0 bar. In other words, what I'm saying is that in this case, so let me write this down as a theorem. Let's see if I have to say it properly. Okay, let me give a proper definition of the setting that we have. So let me write the definition. F 0, 1 to 0, 1 is called the full branch piecewise expanding map if there exists disjoint open intervals. So it's a little bit tricky to say. I want to describe this situation here. I want to describe the fact that I have intervals that intersect only on the boundary, and on inside each interval you have a diffeomorphism here. So disjoint open intervals. So I say that there are open intervals, I0 to I k minus 1, and lambda greater than 1, okay, such that we have that for each I, the closure, so let me write it like this actually, this is not very good. F from I to the open interval 0, 1 is a C1 diffeomorphism. Which admits C1 extension to the closure I bar I. Okay, so this is just a little technical point. When you have some map that is C1 on an open interval, it does not always automatically imply that you can extend it differentiably to the closure. Okay, so this is just to be completely precise. And then we have that this derivative f prime of x is greater than or equal to lambda greater than 1 for all x in the union of all of these. And then we have that the union of all of these equals to the interval. So the union, so the closure I0 union ik minus 1, the closure of this is equal to the interval 0, 1. So what I've described here is just a generalization of this. Okay, maybe let me draw the general picture. Is that we have I0, I1, I2, I3, I4. Okay, and then on each of these we have C1 diffeomorphism something like this. Okay, that's just exactly the same generalization as before. First I do the 10th map where the derivative was constant and the two I0s and I1s are the same, but you can see that this is exactly the same situation as before. Before, if I make some gaps, if I leave some gaps between I0 and I1 and between I1 and I2, I have exactly the general situation that I showed before, and what I'm doing is I'm just closing all the gaps. Okay, I try to describe it in detail in the case where there's only 1-2 branches because it's easier to see, but everything works exactly the same in that case. Okay, and what I explained here is that the effect of closing the gaps is actually very controlled. So in this particular case, you see that also everything, so these points here, they, in some sense, so the full branch, okay, let me explain a little bit the terms. The full branch refers to this property here, so the fact that you have a finite number of intervals and each one maps full branch to all of 0, 1. That's what full branch means. Okay? And piecewise expanding is this second property here, the fact that the derivative is bigger than 1. Okay? And this is simply says that this is an actual map defined on the whole interval, because otherwise, in the cases we looked at before, we didn't need it, we only needed it to be defined on these small finite intervals. Okay, so this is just saying that it's that picture there. And so if you imagine the gaps, then what happens? Then if you imagine as these 2 points as separated, okay, then you can see that in this case, the way that this maps onto the interval 0, 1 is that this endpoint maps to 0, in this case is a fixed point, and this endpoint maps to 1, okay, which again maps to 0. So you have a certain coding. So the point 0 has a certain coding, and the point 1 has a certain coding, which in this case is actually by coincidence kind of is the same as we had before. No, in this case it is 4 followed by 0 recurrent. Okay, this is the coding of x equals 1, and this here 0 bar is the coding of x equals 0. You see this? Yes? Because here we're coding this, we're coding by 5, we've got 5 intervals, so this point here belongs to I4 without any doubts, but then its image is 0, so we have 4 followed by 0. Okay? And now any of these endpoints has two possibilities. Either it maps to 1 or it maps to 0. Okay? In this particular case, it maps to 1. Okay? But here you have two possibilities. You can think of this point as coming from I0, or you can think of it as coming from I1. Okay? When these had a gap, it was exactly the same situation. You just didn't have that ambiguity. When there was a gap, this point on the left definitely belonged to I0, and its image was 1. And the point on the right definitely belonged to I1, and its image was 0. Right? Here, it's a little bit more difficult because here there's a kind of a doubt as to where its image was, right? But when you have the gap, then the point on the left, which belonged to I1, its image was 0, right? Whereas the point on the right, which belonged to I2, its image was 1 because it belonged to this branch here. Okay? And so you can do an analysis of the coding of the way that each point on the boundary of one of these intervals has two possible codings, exactly two possible codings, depending on whether you think of it as being part of I0 or whether you think of it as being part of I1. Okay? And every other point has either only two possibilities. Either every other point never hits any of these points on the boundaries, in which case you don't need to worry about it. Because if you take a point x here and its orbit just stays inside the interior of these intervals forever, then it has a unique coding and you don't need to worry about it. If this point lands on one of these intervals, then it means that this point has two possible codings. Okay? And these two possible codings are consisted of two parts. First of all, one part where it's uniquely defined, which is the 1 million iterates that it stays in the interior, and then after 1 million iterates it falls onto this point here, and at this point it has those two possibilities, so there's two possible codings corresponding to this point. And the property therefore of those two possible codings, even though this point is not on the boundary of one of these intervals, it is in the boundary of one of those much deeper level intervals, right? And so this point corresponds to gluing together 2 points at a deeper level, and it has the property that it stays exactly out. It does not intersect these particular boundary points for a certain number n of iterates, at which point, in some sense, those two boundary points, they have the same sequence, okay? And then at the moment in which it hits one of these 2 points, then it acquires two possibilities for its symbolic coding. So there is a countable set of points which it makes sense to assign two symbols to. Okay, really that's all it boils down to. So the theorem we can show is a slightly different than the topological conjugacy, and what we have here is that if, so let me write this in theorem. If f 0, 1 to 0, 1 is a full branch piecewise expanding, then with, let's say, with k branches, so when I talk about branches I just mean how many of these intervals contains, right? Okay. Then there exists a continuous surjective map pi from sigma k plus to 0, 1 such that H composed with sigma equals F composed with H. So what's the difference between this and the previous one is that this is not a bijection. Okay? Because if I say, okay, what is the coding of this point here? Okay, there are two possible sequences that map to that point there. So this point here has two pre-images in the space of sequence, which are the ones we studied and we analyzed explicitly in detail. Okay, so each of these boundary points will have exactly two, and each of the pre-image of all these boundary points will have exactly two, as I described. Okay, because they will only acquire this problem once they fall onto one of these points in some sense.
Are they topologically not equivalent to the one when we have gap?
No, it's not, because this is no longer bijection between, and also, of course, this is still a Cantor set, whereas this is no longer a Cantor set.
Yeah, it could be that there is another unknown homeomorphism that does the job.
No, because this is a Cantor set and this is an interval. So independently of the dynamics, you cannot have a homeomorphism between a Cantor set and an interval, because a homeomorphism preserves topological properties like connectedness, and it's not like that.
Pi or each
Pi.
and
Oh yes, thank you. Yes, so this is in some sense an a priori problem that I could have mentioned right from the beginning. So if we want to do some kind of symbolic coding, we have the problem that this is a Cantor set and this is now an interval because all the points stay inside lambda, so we cannot have a homeomorphism. Okay, but we have something very close. So that's what I was trying to explain, is that really the difference between a Cantor set and an interval is just gluing all the boundary points to each other. When the Cantor set is embedded in the interval, then you have this notion and you can glue them together. So we can be a little bit more specific and say that because of this conjugacy, because there's a continuous surjective map, we still have certain properties of the dynamics apply, right? For example, the fact that because we still have this property, this is called, i.e., this is called pi is a semi-conjugacy. Between F and sigma. So semi-conjugacy means this. Means that you have a continuous surjective map. Okay, this is the definition of semi-conjugacy. So it's a slightly weaker than the conjugacy, but it's very useful, and you can show that this still allows to transfer some of the topological properties of the dynamics here, because you still have this property, and so in particular you still get, and I will leave this as an exercise again, we have the periodic points F are dense, okay, periodic points are dense in 0, 1, and F is transitive, so we have dense orbits. Okay, because this is a continuous surjective map, so if you have a dense orbit here, you have a dense orbit here, and you can still push some of the topological properties of the dynamics on sigma to the dynamics on lambda.
This is very similar to the map we considered at the beginning, 10x mod 1.
Exactly. So let's actually use that. Maybe I should have used that one as an example. So what is the coding? So let's look at 10x mod 1. So we have 0, we have 1. So here we have 0.1, 0.2, 0.9. Okay. So let's try to do the coding. Okay. Okay, so what is the coding of 0? Yeah, because it's a fixed point, 0. Okay, just like in the other cases. So here we have 0 bar. What is the coding of 1?
1, 1.
No. 0, 0.
No, but
What are the intervals? How many intervals do we have? So this is I0, I1, I9. We have 10 intervals, right? I0, I1, I2, I3, I4, so on. This is here is some, for example, I5 goes from 0.5 to 0.6. This is I5. You agree? So So this is I9. So what is the coding of 1? 9 recurring. Because this is also a fixed point. Okay? So what is the coding of this point here?
Which one?
0.1.
1.
So we have two possibilities, yeah? So if we think of this as coming, think of the gap. Think that you are just making a little gap, just as you think about it, right? So now, if there was a gap, then this would be the point on the left, would be in I0. And then the image of it would be 9, right? So this has two codings. One is 0, 9 recurring. And the other one?
1, 0 recurring.
Yes. 1, 0 recurring. What about this point here?
It would be 5 0 recurring and also 1 where
you see the pattern? What if we take the point 0.8? I didn't do it a very good scale. 0.8 has also two possibilities: 7 9 recurring and 8 0 recurring. And what about the point? So what are actually the decimal expansions of these points? These are the decimal expansions of these points. Yeah?
yeah.
This is exactly the decimal expansion of these points. So these points have two decimal expansions. As you know, decimal expansion is not unique for some points. For which points is the decimal expansion not unique?
The one which lies on the boundary of the intervals we have.
Exactly.
Yeah.
Exactly. Yeah? Those, the decimal expansion, the two decimal expansions are those that finish with all 9s or finish with all 0s. Then you can write it like this. Then you can write either 5 all 0s or 4 all 9s, and you have exactly the same point. Okay? And that is exactly because the real numbers are a Cantor set with all the gaps squeezed. Right? That's exactly what they are. So this is exactly how you can recover the decimal expansion of the numbers. We're going to go back to this in the ergodic theory course. So actually this observation here is very relevant. Okay, we're going to talk about this in the ergodic theory course. But so this is a very good example. If you get a little bit lost with this, you know, as you're going through it, use this 10x mod 1 to get a better feeling, right? What happens when you go to the deeper level, right? To the next level, you take this 0.506, 0.5, 0.6. Okay, this one, as we said, has these two possibilities: 4 9 recurring and 5 0 recurring. And this one has also 10 subintervals, right? So this one is, for example, 0.53. 0.53. Well, I'm not already writing 0.53. So what are the possible coding of that point? So here we have 0.53. What does that mean? That it's on the boundary of these 10 intervals of the next level. Okay? So this one, we can write it either, or let me do it somewhere here. So 0.57. So here we can write either 0.579 or 570 or 0.569 for this point here. Yeah? And that corresponds, it's exactly the structure I said. Remember, there's a certain number of iterates where they will be the same. So any point that looks like this will have the structure 0.327152, and then you will have 9 recurring, or 0.327153 recurring. Okay? So any 2 points that are identified will have this structure. They will have initially a certain number of iterates in which they coincide, and then they will have either of these two possibilities. Okay, in the example we just did with 0 and 1, so it was a little bit misleading because here you could only have 0, 1, but in general you could have, for the next step you could have everything, and then you have exactly the two codings of the endpoints. Yeah. Okay. So now the final step is we actually want to code two maps like that, right? So the symbolic dynamics is a way to understand the properties, but what we would like also is to say that if we have two maps like that, so let F, G be full branch. So this is another theorem, okay? F, G be full branch, piecewise expanding. Okay, and then I might need to add another assumption here because of what I would like to say. Okay, with the same number of branches, okay, then F is topologically conjugate to G. Topologically conjugate. Okay, in other words, I have two maps. Now, is this true? So, I have two maps. Like this. And then I have one that has different size branches, right? So one maybe is very small, maybe one is very small here. So we may have this. Okay, the question is, are they topologically conjugate with some H?
Yes.
Why?
Because this is a theorem.
So basically, here it's a little bit, it's not automatic, right? Because what we've shown is that there's a continuous surjective map. So here we have sigma k plus in both cases. And we know that we have this map here. And we know that we have this map here. This is pi f, so this is f. This is g. This is pi f's from this theorem here, right? That gives this conjugacy. And this is pi g. But these are not bijections. These are just maps that go from here to here. They're not invertible. Right? So we cannot directly just say, okay, this is conjugate to this is conjugate to this, so we take the composition. But can we take the composition here? Can we take pi f minus 1 composed with pi g and get a bijection between these two? What we want is a conjugacy. So we actually want a bijection between these two.
Yes, because it is fine except at these points where we have the mean, and at that we don't care about the representation because whatever representation we take, we will just map the points to itself, to the other one.
So as long as they map to the same, as long as when you have two sequences here mapping to a single point here, you want to make sure that the same two sequences also map to a single point there. Right? If everything matches up, then you can do it because you say, okay, most points anyway, they have a single point, and so it's well defined here. But some points, they have two preimages. If these two preimages map to a single point here, then you can smoothly go from there to there without any problem. Okay? So under what conditions will this happen? How do we know if the same two sequences that map to a single point here also map to a single point here? Sorry? Not completely. That's not completely enough. So first of all, the number of branches is necessary for the same reasons. Why? If they don't have the number of branches, they cannot be topologically conjugate. Why is that? Number of fixed points. Okay? So the fact that they have the same number of branches is a necessary condition. It is not completely sufficient. There's still a little bit of an issue. We need to check. Sorry? Sorry?
That they are glued together.
That they're glued together in the same way. Right? So for example, if we had this, then it's not the case, right? Because this point here, you have a kind of, you need to switch the orientation from here to here. So this point here has a coding 0, 1, 1, 1 because it maps to here, and that would be, but whereas this point here has a coding 1, 1, 1, 1, Okay, and if you check, you do it at home again, you should do it yourself. You can see that in this case it doesn't match up because you get a different you get a different ordering of the embedding. So this is a kind of same. You take the symbolic dynamics and you embed it in here. So every point here has a certain coding. Okay? But the coding, when you look at something like this where all the branches are orientation preserving, everything kind of, the coding is a kind of monotone in some sense. You get the coding that you expect. But when some of the branches are orientation reversing and some are orientation preserving, it gets a little bit tricky because here you have 2 points that you have both from the left and from the right you map to here, whereas here it's this point that maps to 0, not the same point here. So it's as though this embedding switches, compared to this, for this particular block, it switches everything around in a different direction. And so you cannot match them up and get this. It would take a little while to write it down formally, so I would like you to do this at home to check. Okay? So what we have to add is that the easiest way to say it, it's not the most efficient way, is that the same number of branches with corresponding, such that corresponding branches have the same orientation. Okay, so you take 1, 2, 3, you put them in order, these branches, and they all have to have the same orientation to each other, and then you can guarantee that you get exactly this, all the codings, all the combinatorics match. Okay, and I want to finish, I know we have just a few minutes, with really, in some sense, the theorem that motivates all this, because you could argue that these are all very special cases, these full branch maps, and so on. And I want to argue that they are, in some sense, very natural. And so, I'm going to say the following. So let f from S1 to S1, so I take the circle, and I define a map on the circle, be an expanding map. C1, expanding map. In the sense that, okay, expanding means that f prime of x greater than or equal to lambda greater than 1 for all x and x1. The derivative is bigger than 1. So what does it look like, a C1 expanding map on the circle? What can it look like? Let's try to draw a graph. You know that the graph, so let's think of this as the circle. So we cut the circle at some point, 0, right? We cut it out, so 0 is identified with 1. That's what makes it a circle. Okay? So the graph of the map, so we have the circle here, we have S1 here, we have S1 here. These 2 points are identified, but we can still draw the graph of this map, right? So that whatever this point 0, it will go somewhere, right? So it will go somewhere, okay? And then it's expanding, so the derivative is bigger than 1, okay? And because it's bigger than 1, what happens? We will hit the top, right? We cannot cross all the way from here to here without hitting the top. Why is that? Because it's C1 and it's expanding, and so again it's a mean value theorem, right? Because the derivative is bigger than 1 everywhere, so if you look at the image between these 2 points, then its image in some sense must be bigger than 1, right? You cannot, if we went from here to here, then the distance in the image would be less than 1 and it could not be expanded.
Actually, because it is S1, the value at 0 must be the value at 1.
Exactly. So that's even better. Yes. So it cannot go like that. Exactly. Okay. So that means it must hit the top. Okay, but this of course is identified with this because this is the circle. So then now, let's say it hits the top again, it hits the top a few times and then it does this. Well, in this case maybe it needs to hit the top again and then it does this. Does this look like a full branch piecewise expanding map? Not as I've drawn it, but I chose the wrong place to put my 0, right? Because this has some fixed points, okay? And let me shift, let me say, oh, wait a second, now that I know that there's a fixed point here, let me call this point 0, and not that point, okay? And then the picture would be different, because then the picture would be, if I know that I start with 0 at the fixed point, then that means that the picture, this is 0, this is 1. I start with 0 at the fixed point, right? So this must do something like this. And then it must finish here, which is identified with 0. Okay? So every C1 expanding map of the circle is a full branch piecewise expanding map of it. It has this structure, necessarily for topological reasons if you want. So what does this theorem imply about two? This means in particular that every C1 expanding map is a covering map of the circle. Okay? The number, in some sense, it covers. If it has 3 branches, that means that it has a degree 3. It's a covering map of degree 3, in the sense that it covers 3 times. Right? The image of the circle covers itself 3 times, like this. And if you take any C1 expanding map, it's a covering map of the circle, so it's got a certain degree, at least 2, as we said, because if it was 1, it cannot be 1, right? It needs to go at least twice. And so what is the consequence? That if you take 2 C1 expanding maps of the same degree, then they will be topologically conjugate. Right? Because if you take another expanding map, this expanding map, let's say these were 2 different expanding maps, you shifted a little bit. In this case, the branches all have to have the same orientation because it's a C1 expanding map. So these will be satisfied if it's got the same degree, they will have the same number of branches, they will have the same orientation, and therefore they will be conjugate. Okay? So this gives a complete classification up to topology. Remember, this was always our original concept, is we're trying to classify. This gives a complete classification up to topological conjugacy of all C1 expanding maps of the circle. Okay? The topological conjugacy class is determined simply by the degree of the map, if it's a C1 expanding map. Okay, so corollary, let me write that down. There's 2 corollaries that are important. So corollary of this one is that all C1 expanding maps of S1 with the same degree are topologically conjugate. And the second corollary, which is, again, in some sense, even more what we really want to do, has to do with the structural stability. Again, remember, one of the things we said, one of the main interesting applications of the notion of topological equivalence classes, topological conjugacies, is that you ask if a system is structurally stable, so you take a perturbation and you ask if it is in the same topological conjugacy class. Okay, and that's when you call it structurally stable. Okay, so for C1 expanding maps, you have the usual topology, so you can let's write C1 of S1, okay, for the family of all C1 expanding maps of S1, okay, and then there is a natural topology on this. What's the topology on this? Just the C1 topology, the same one that we saw before, right? Because we can write we can draw any of these as a graph, just like we did before. So, okay, it's going to look something like this. And notice that because it's C1, then this is not really, when we do these, when we define this full branch piecewise expanding maps, we don't say anything about the relation between the derivative here, the derivative here, here. They can be completely different. But this is C1, these 2 points are identified. So this derivative here, this is differentiable at this point, right? So the derivative from the left is the same as the derivative from the right here. It's differentiable everywhere. And here also, it's always the same derivative. It's differentiable everywhere. So we can just define the C1 metric, right? We can put the C1 metric, D1, the C1 metric. So what happens if you take a C1 perturbation? What happens if you start with some map like this G, F, okay, and you take another map that is C1 close to this one? You necessarily get another map that is still C1 expanding map of the circle, because you have your map of the circle. You perturb it a little bit, which means you will get something that might no longer have a fixed point there, but it still will look something like this, right? And now, and at every point you will have the maps. The graphs will be close, epsilon close, and the derivatives will be epsilon close. Okay, so then you just shift a little bit the initial point, and you get again your 2 full branch expanding maps that are topologically conjugate by this theorem here, right? And which means that if you take a small C1 perturbation, it will stay within the topological conjugacy class necessarily. Okay, so this implies that every map, so all maps F in C1 S1, maybe I should put expanding. Usually C1 X1 is just all maps. So the expanding maps of the circle are structurally stable. And now this structural stability is much less obvious than the other one, because you have so many different orbits here, right? Remember the dynamics of these systems. We have infinitely many periodic points. We have infinitely many orbits we have dense orbits. We've not emphasized it, but we have infinitely many dense orbits, okay? So when you say structurally stable, you say, okay, I shake this system a little bit. How can I be so sure that every single one of those orbits is still there? That's what I'm really saying, right? So one thing is to say, well, you take these intervals, the systems we looked at before, which are basically, everything is converging to a fixed point or coming from a fixed point, everything stays conjugate. But here you have all these periodic orbits, all these dense orbits, okay? So if you just think about it like that, when you have all these orbits and you say, okay, you perturb the system, what you're really saying is that every single one of those orbits survives this perturbation. They just move a little bit, but the whole thing just moves a little bit. You cannot have some big bifurcations of things changing. Okay? So this is the conclusion. This is the conclusion. In some sense, the real theorem of everything is that expanding maps of the circle are structurally stable, which is a remarkable theorem, and everything else is somehow developing the techniques and the tools and information that we need for this. But of course, these similar techniques and tools, they apply also to many other systems, actually. Okay? So this symbolic dynamics is a technique that can be used in higher dimensional systems, systems that have this hyperbolicity that was being talked about at the seminar today, where you have some expansion in one direction and contraction in other direction. So there are many, many situations in which you can do this kind of coding, and you can use this coding to study structural stability and topological conjugacy class, okay? But there's many systems where you cannot. So here, mathematics is all about you use a technique, you look at all the systems, and then you find some systems where you can no longer use, and you develop some new techniques. Okay, but still this is a very important class. Okay, thank you. So this more or less concludes this topological part of the course. Okay, so we will start studying these maps from a more probabilistic point of view.